All right, now let's talk about computation graphs. The problem we want to solve at this moment is how we can compute gradients for our models. We have seen score functions and loss functions and regularization loss. And the total loss was data loss plus regularization loss. And if we can compute the gradient of the loss in respect of our parameters, then we can learn W1 and W2. However, these equations look quite complicated. How do we compute gradients? A bad idea is derive the gradient of L in respect of W on paper. We just expand these equations and see how they are represented with our parameters like this, and add all and calculate the gradients. However, the thing is, this process is very tedious. It requires lots of matrix calculus and needs lots of paper. Another problem is, what if we change the loss? Then, for example, we originally used softmax loss. However, we just want to change to SVM. Then what happens is, we need to redrive all these equations from scratch again. And the third problem is that this process is not feasible because nowadays we have very complex models, and calculating these gradients for our model is infeasible. For example, the very first deep learning network came out in 2012, AlexNet, has this architecture. From input, we have a lot of weights and the loss function. This one is the very first model, but it still looks quite complicated. And nowadays, we have even more complex networks. And even more like this. And a better idea to calculate the gradients is by introducing the concept of computational graphs and use backpropagation. And what is a computational graph? For example, let's say our output F is calculated by matrix multiplication between W and X. And we plot this computation process with graphs. Here, X and Y, W are here, and they are multiplied. And after that, score is calculated, and we apply hinge loss, which is SVM loss. And W goes through another computation process to calculate the regularization loss. And these two values are added, and this results in the loss. Therefore, computational graphs are nothing but representing all these computational processes in this graph format. I'm going to show you a very simple example. Let's say our function f receives three variables, x, y, and z, or x, y, and z vector. And we can represent this as this computational graph. X and y get added and results in q, and q and z are multiplied to get the final value, f. And for example, if x value is -2 and y is 5 and z is minus 4, we just put down these values here. And the line contains the same values. It's like circuit. And after that, q becomes 3 because we want to add these two values. And after multiplying these 3 and minus 4, we get the final value, minus 12. And when we want to calculate the backpropagation or gradient for all the components, we're going to calculate first local gradients. Here, x and y get added and results in q. And we're going to calculate local gradient here. Q derived by x and q derived by y, like this. And here, this is 1, this is 1. And then we're going to calculate local gradient at the next step, here and here. If we derive f in respect of q, it's going to become z, and z becomes q. So this is the derivative. And what we actually want is the derivative of f in respect of x, y, and z. And how do you calculate this? This step involves derivative of f in respect of f, which is going to be 1. So we put down 1 here. So the top numbers are the actual numbers we put. And this process is called forward path. And the next thing we are doing is backward process. So for forward process, we are starting from input values and get the final value. However, in the case of backward path, we're starting from the top and go backward and calculate the gradients and write down the resulting numbers at the bottom of the resulting values, like this. So we are starting from the very top, and we need to calculate the gradient or the derivative of f in respect of f, which is 1. And here we want to calculate derivative of f in respect of z. And how can you calculate this one? Here, derivative of f in respect of z was q. And here, q is 3. So we're going to write down 3 here. And the next step is df dq, which is z. And z has the value of 4. So we're going to write down minus 4 here, like this. And how do you calculate derivative of f in respect of y? We are going to apply the chain rule. Chain rule states that derivative of f in respect of dy equals, we first derive f in respect of q, and we can view this as upstream gradient. So gradient is flowing from the top, and the local gradient dq dy is multiplied with the upstream gradient. Then we can get the gradient of f in respect of y. And this was 1, this was minus 4. So we can put this value here, minus 4. And similarly, x has the same architecture. So minus 4, 1, and it's going to become minus 4. In this way, if we are following this backpropagation computational graph, we can calculate all the gradients all the gradients of the loss. So this is what we are actually doing to implement our neural networks and our other models. In other view, you can view this as we calculate the local gradients and multiply these values with the upstream gradients. And upstream gradients is the gradient of the loss in respect of the upstream variable. And if we multiply these values together, then we can get the gradient of the loss in respect of this local variable. Hence, we are using downstream gradients with upstream gradients. We are applying chain rule over and over. That's the strategy. For y, we do the same thing. And this gradient becomes upstream gradient for the next step. It was originally downstream gradient. However, it becomes an upstream gradient for the later layers. Another example is this logistic regression. Here we have 5 variables, W0, X1, X0, W1, X1, and W2. They get multiplied, added, and multiplied with -1 and exponentiated and get added with 1, and then it becomes a rate. We take the ratio. And let's say these 5 variables have these values. Then doing the forward calculation is quite straightforward. We just need to follow these computation steps. So multiplying these two results in -2, multiplying these two results in 6, -3, add all these numbers, 4, like this. It's quite easy to do this. Okay? And now, I'll stop this video and take some time and calculate the backward path on your own. And then check your answers with mine. The starting point here, DF and DF, is 1. It's always 1. It starts from 1. Okay? So take your time and calculate the gradients, backward path, and then check your answers with me later. All right, have you calculated the backward path on your own? To calculate the gradients, we need to use these derivative rules. When you derive the exponential function, it is just itself. This one becomes a because we need to remove x. And this one becomes, c plus x becomes 1, like this. I guess you all know this. How can you calculate the gradient at this point? Here we need to use this value and this one. And upstream gradient is 1. So local gradient is 1 divided by 1.37 squared. And it becomes minus 0.53. And what about at this point? We need to use this rule. So the upstream gradient just comes here. Local gradient is 1. Upstream gradient is minus 0.53. And this part, upstream gradient is this one, and the local gradient is e to minus 1, e to the minus 1. And that becomes minus 0.2. Here, we just need to pass the value a, and local gradient is minus 1, and the sign is reversed. Here, we're just adding, and this gradient is just distributed 2 and 2. Local gradient is 1. So this plus operation is like distributing this gradient to or multiple paths. This part W0 times upstream gradient. Okay, so that's the result of all backward paths. Another thing I want to note here is that computational graph representation might not be unique. There might be multiple ways to represent the same computation. And we are going to choose one where local gradients at each node can be easily expressed. And this is the sigmoid function, this part. And we know that the derivative of sigmoid is 1 minus sigmoid times sigmoid. So here, the input is 1, then we can just calculate the sigmoid value and put the values here. Then we can easily calculate the gradient. What I mean by that is, because we are adding this 1, the local gradient can be 1 plus e to the power of minus 1 and 1. So we're going to subtract this value from 1 and times 1 plus e to the minus 1 over 1. And we already calculate this value. And it's going to be 0.73. Here, this is the resulting value. So it's like sigmoid minus 1 plus 1 is 0.73. So we can use this value to calculate the gradient here. It's going to be 1 minus 73.73 times 73, which is 0.2. So they basically have the same value. Like when we divide the calculation steps or not, they all result in the same value. And you might have noticed this. There are some patterns in gradient flow. The AND gate is a gradient distributor. The upstream gradient get distributed equally to the downstream lines. And MUL gate, multiplication gate, swap the values. 2 goes here, 3 goes here, and they get multiplied with the upstream gradient. And copy gate is gradient adder. So the gradients from this and this lines get added. And the max gate is a gradient router. Only the value, only the line having the maximum value receives the upstream grade. Other one receives 0 gradient. Okay, so when we try to implement this using Python, this is one example of implementation. S0 is W0 times X0. So here, this is S0. This one is S1. And S0 plus S1 is S2. And when we add these two values, this becomes S3. And after sigmoid, this one becomes loss. And how do you calculate the backward path? Using to compute the gradients. The gradient L at the last step is 1. It starts from 1. And grade S3 is using the upstream gradient and the derivative of the sigmoid function. And W2, because here we have adder, receives this gradient. So this gradient goes here and here, because AND gate is like gradient distributor. So W2 and S2 receive the same gradient like this. And S0 and S1, because this is also AND gate, receive the same gradient S2, S2 like this. And gradient W1 is calculated by gradient S1 times X1, X1, W1 like this. Similarly, W0, X0, X0, W0. This is how we can implement the gradient or computation graph for our sigmoid function. So this is the base case. We follow sigmoid. We deal with the AND gate, and then another AND gate, and multiply gate like this. Okay. And as you can see here, when we try to implement this multiplication or adder other components, we follow the modularization process. And this is a rough pseudocode. We distinguish the forward pass and the backward pass. We receive input values and calculate the final value. Here, we need to topologically sort our nodes. However, when we are doing backpropagation, we need to reverse the order and then calculate the backward process. Okay, so forward and backward have the opposite direction, forward and backward. And this is the actual PyTorch code. Another thing you need to note here is when we're doing forward calculation, we need to save some values or cache some values. Because as you see here, to calculate the gradient of x1, we need to know the value of w1. And for w1, x1. And we need to save these values for backward pass. So that's what this is doing. Save some numbers for backward. And backward receives the stored value and calculate gradients using the upstream and local gradients. Here we always receive the upstream gradient. And after we implement all the computational blocks following this design pattern, then we can just connect all these modules or blocks to construct our model. Then the only thing we need to do is just perform the forward pass, and after that, you perform backward pass, passing the gradient, upstream gradient. Then we can update all the modules or all the blocks. Okay, that was about computational graphs. And let's implement some of the modules together. Okay. First layer we're going to implement is multiplication layer. We need to have initializer. The next thing is forward. And multiplication requires two numbers because we need to multiply two numbers. And last, we need to implement the backward pass. To do so, we need to receive the upstream gradient. Okay, let's implement the initializer first. We need to store both the x value and the y value. However, at the initialization step, we don't know exact values. So we are going to initialize them as none. And for forward, what we are going to do is we need to store the x value and the y value, because these values are required to calculate the backward pass. And the output value is very simple, just x times y, and we're going to return this value. For backward, what we need to do is dx is going to be the upstream gradient times y, because multiplier swaps the values. And dy becomes dl times self dot x. And we're going to return the x and dy. That's all. So different from just naive implementation, what you need to remember is you need to store the values that you would need for backward pass. Okay. Another class we are going to implement is add layer. Of course, we need to have the initializer, the forward pass. We need to receive two numbers because we need to add two numbers, and backward method. And we need to receive the upstream gradient like this. And this is going to be our PPP exercise. Take enough time and try to implement this layer. And when you are implementing this layer, keep in mind that what you should store for backward computation. Okay.